Hello, everyone. Welcome back to Python Challenge for All. Okay, let's continue. Last time we started to explore about interesting aspects of bits, bit operations. So yeah, as I explained, usually we use decimal counting. So meaning we use 10 as a base. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And after adding, after 9, we have 1, 0, which is like to the two digits. Okay, so that means in decimal, we use 10 symbols from 0 to 9. Instead, in binary counting, binary representation with only two symbols, 0 and 1. And here, as we saw, it's expressed as series of zeros and ones. And there's only unique way to express any number in this binary representation. And usually in Python, binary representation is preceded by 0b to express to express that it is a binary representation. And I explained how to change from decimal to binary, and also binary string to decimal. And also at the same time, we talked about hexadecimal representation, which uses 16 symbols from 0 to 9 plus A through F. Okay, so and 0x is usually used as a prefix to say it is a hexadecimal number. At the same time, after that, I explained about bitwise operations like not, and, or, and exclusive or. And also bit shifts operator and bit shifts assignment operators like these. Lastly, I explained about how to do the count the ones in, say, decimal representations. I will come back to this point later at the end of today's lesson. Okay, let's go on to today's part. Lesson 103, playing with bits. The second topic is odd or power of 2. Okay, so think about it. Task 1. How can we find out whether any number is odd or even using bit operations? Okay, this is a simple way. Usually in decimal, we use %2 and see the remainder. If it's 0, it's even. If 1, it should be odd. But using binary, there's another way to see. In binary representation, the LSB, least significant bit, meaning the rightmost bit. For example, in this case, this one is called LSB, least significant bit. On the contrary, this one is called MSB, most significant bit. So the point is, if LSB is 1, it is odd, and if it is 0, it is even. So so let's go back to the code and see. So any number n equals, say, again, 123. If to see the least significant bit of any number is taking and with 1. Okay, so if it is, let's run it. If it is 1, it is odd. And if it is, let's see, in this case, will be 0. Just like this, it will be even. So it's always the same as n %2. Yeah, like this. So they are all the same. If it is even, it will be 0, and if it is odd, it will be both 1. Okay, that's the first point. Okay, check with n and %1 will give the answer. That's the simple way to check it. Next task is n a power of 2 using bit operations? You know what power of 2 is. It's like 2, 4, 8, 16, 32, 64, 128, 256, and something like that. They are kind of a special number because they have all zeros except for MSB. So let's see that. For any n, for any I, let's write this way. For any I in range, say, 10, okay, colon. So to print, let's see what we have here as 2 to the power of I. 2 raised to the power of I. And at the same time, let's write the binary representation of those numbers. Okay? So if we have all these, we see that it will be like this. So 0B1, 0B10, 100, 1000, and all the way up. So this is how you can see to see how they are powers of 2. So the next task is, how can we do this? How can we do if any number is power of 2 in very simple operation? Okay, so actually, interesting thing is that n minus 1 has all lower bits set to 1. So for example, if you see, okay, let's write this way. The number, we first calculate the number as n equals 2 to ith power, okay? 2 raised to the power of I, so of course lower. And then we print n, binary n, and n minus 1, and binary n minus 1. So let's see what they look like. So, okay. So n minus 1 is like, this is exceptional, okay? 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. Okay. So kind of these are complementary, okay? So the point is, if you take n and n minus 1 and calculate AND operation, the result of AND operation, it will be all 0, only if n is positive. So let's see. It's right that way and check. So in this case, okay, let's write even more. So let's write this one. If n is positive and n ampersand, this should be not and, but this should be and. Okay, and operator. And this should be ampersand operator taking the bitwise and of. So let's take this way. Okay. So this will, let's print it. Take all these numbers are, okay, equals 0. Okay, so sorry, this should be, okay, so this should give all true. So this is the way to check whether they are powers of 2. For any number, of course, say n equals 123, which is not a power of 2. If we print it, if we copy and paste it here, like this one, it will give false. Okay, so this is a way to check whether any given n is a power of 2 or not. Okay, interesting. So you see how the binary representation of these powers of 2 and powers of 2 minus 1 look like. They are only MSB is on, and in this case, all the bits are on. 1. Okay. Okay, let's go back to the final question, which is from last lesson. Count the number of 1 bits in the binary. So using this can be done using this kind of story, this kind of logic. So we can count by shifting, combining, and shifting. Okay, let me explain this way. So for any number of, say, n equals, again, 123, you know what, print n and binary n, okay? So for here, we calculate like this. We initialize counter as 0, and while n is greater than 0. Or we can write this way, okay? While n is not 0 or positive, we count if count equals n ampersand 1. So this will be counted up only when the LSB of that new n is 1. Okay, and then we shift operate equals shift 1. So this will give the number of ones in binary representations. Lastly, we print CC. To check that, we also print n. It should be 0. Okay, let's see that. This was wrong. Okay, so this should be shift n 1. Okay, and lastly, print n and c. CC, sorry. CC. So by doing this, we can count number of ones in starting n as 6. And finally, of course, n is 0. This works for any number, 1, 2, 3, 4, 4, 5, 6. And we have we have all the count numbers at 6, like this. Of course, we can each time print CC and n and CC like this. Okay, so that we can follow the process. Okay, maybe we should write binary representation of n rather than n. So as you can see, each time we see the LSB and see if it's 0 or 1 and shifting it to the right. And that will count up the number of ones in any representation of binary n. Okay, bit confusing. I hope you will review and see the points. Okay, I will continue this kind of topic next time. Please come back. Bye-bye.